The universe started almost empty, just about nothing. In that first instant, the whole future was set by vibrations. They were smaller than an atom. So the story is how these tiny ripples, after the Big Bang, turned into the biggest galaxy clusters. And you end up seeing the universe not as random lights, but as one structure. It's growing. It has a clear starting point. You trace it back. Random quantum whispers frozen into space. Then gravity pulls on them. For billions of years, gravity sculpts them into the largest things we can see. And you look at the night sky. You see stars. But you're also seeing an echo, the echo of how it all began. That near-perfect smoothness is the most important thing to remember. For a long time, scientists looked at that early universe and saw a problem. If everything was so smooth, so evenly spread out, how did anything ever clump together? Gravity pulls matter toward other matter. But if all matter is spread perfectly thin, like a single coat of paint on an infinite wall, then gravity has nowhere to start. There's no slightly denser spot to begin the pull. Under those perfect conditions, the universe would have just remained a featureless, expanding fog. Silent and dark, a cosmic dead end. So the fact that we are here looking up at a structured sky with galaxies tells us one thing: that early canvas was not perfectly blank. It had to have tiny flaws, minuscule wrinkles in the fabric of space itself, and these weren't random accidents. They were the universe's opening notes. The first gentle hum of a symphony that would take billions of years to play out. To find where galaxies come from, you have to look for the origin of that first, essential imperfection. The birth of galaxies starts with the birth of the universe. In its very first fraction of a second, that's where the leading theory goes, into quantum mechanics. In the subatomic world, nothing is perfectly still. Empty space isn't truly empty. It's a seething sea of potential. Pairs of particles and their opposites flicker in and out of existence. These are quantum fluctuations, brief, random variations in energy, the universe's most fundamental whisper. Then picture the cosmos in that first instant. A period of exponential expansion called cosmic inflation. Space itself stretched faster than light, and in that violent growth, something happened to those quantum whispers. A microscopic fluctuation, a tiny hiccup in energy that might have lasted a moment. It didn't have time to fade away because space expanded explosively around it. That tiny imperfection was stretched, magnified from a subatomic speck to a scale encompassing vast regions of the young cosmos. A random, fleeting event became frozen into the geometry of spacetime. Etched there permanently, this process happened everywhere all at once. It imprinted a unique pattern across the entire universe, a faint tapestry of slightly denser spots and slightly emptier patches. Often called the universe's fingerprint, it wasn't a design, it was a record of quantum randomness blown up to cosmic proportions, these minute differences in density. These primordial seeds, they were the only instructions gravity would ever need, the starting points, subtle cues written into the fabric of everything, marking where the great cosmic construction would one day begin. A whisper frozen in space is still a theory. To prove it happened, you'd need a photograph. And there is one, a picture from when the universe was 380,000 years old. It's the oldest light we have, it's everywhere, the cosmic microwave background. The universe's first portrait. Before that, everything was a hot, dense fog. Particles and light packed so tight light couldn't travel, just a glowing, opaque soup. Then expansion cooled things, a transition happened. Electrons and protons combined. They formed the first neutral atoms, and the fog cleared. Light that had been bouncing around was finally set free. That first flash of transparent light has been traveling ever since, stretched by the expanding universe into microwaves. It's a fossil of that first moment of clarity, bathing the whole sky in a faint, cold glow. And in that glow there's an imprint, the pattern. When satellites like WMAP and Planck mapped this radiation, they didn't find a uniform blanket, they found a mottled sky. A tapestry of subtle temperature differences, warm spots and cool spots, variations of just a few millionths of a degree, but they are everything. A slightly warmer patch means the photons there had to fight their way out of a slightly denser region of the early plasma. A cooler patch marks a slightly emptier void. These tiny temperature differences are a direct map, a one-to-one map of those primordial density ripples. The quantum seeds written in light, this map is our Rosetta Stone. It confirms the universe began with those subtle imperfections. The pattern predicted by inflation matches the pattern in this ancient light. Stunning accuracy. We're not just theorizing about the universe's infancy, we're holding its baby picture, and in the faint blotches of that picture, you can see the blueprint. The blueprint for all future structure. Every galaxy cluster, every filament of the cosmic web, every empty expanse, they all trace back to a specific, slightly warmer spot on that microwave map. The connection is that direct, the evidence is that profound. We've seen the seeds, frozen in the first light. So then the question becomes, how did these faint blueprints grow? How did they become the universe we see today? The blueprint was there, written into that ancient light, but a blueprint isn't a building, you need a builder. And the builder for the universe was gravity, just this patient, relentless force. In the beginning, everything was still this almost smooth sea, dark matter and hydrogen gas. Nearly uniform but not quite, because in that faint pattern from the cosmic microwave background, some spots were denser, just a fraction of a percent denser. An almost insignificant difference, but for gravity it was enough. In those slightly overdense regions, the pull was a little stronger. It started this whisper-soft tug on the material around it. Think of a shallow hill on a vast flat plain. Even a slight incline makes water flow toward it. Matter drifted the same way, imperceptibly at first, toward these denser knots. That's gravitational instability. It's not a sudden collapse, it's a slow, cumulative drift, a tiny advantage that compounds over time. A region with a little extra mass attracts a little more gas, a little more dark matter. That makes it denser, which increases its pull, so it attracts even more. It's a self-reinforcing cycle, a snowball rolling downhill for millions of years, then billions. The dark matter formed these vast, diffuse halos first, invisible frameworks, gravitational scaffolds, and they guided the ordinary hydrogen gas. The gas flowed into these growing wells of gravity. It began to heat up, it began to swirl. This was the quiet, foundational work, laying the cosmic groundwork, all of it driven by that patient, persistent pull. Turning quantum whispers into the first whispers of structure in the dark, gravity had its starting points, but there was a cosmic deadline. The ordinary matter, the hydrogen and helium, it was under immense pressure. In that hot early era, light and matter were locked together. Radiation from the glowing plasma was pushing back against gravity's pull. It was like trying to build a sandcastle as waves crash over it. The gas couldn't settle, it couldn't collapse into dense structures, not quickly enough, not in the time the universe has existed. The math didn't work. Something else had to lay the groundwork first. That something is called dark matter. It's a mysterious, invisible substance. We know it's there from its gravitational pull. But it doesn't emit or absorb or reflect any light we can detect. It's truly dark, and it's cold, meaning its particles move slowly. That's its crucial superpower. Because dark matter doesn't interact with light, it's immune to that early radiation pressure. While ordinary atoms were being buffeted, dark matter was quietly responding only to gravity. It could begin clumping together almost immediately. Billions of years before the first stars, vast clouds of dark matter were already coalescing. They formed immense, invisible halos. Gravitational wells, think of these halos as templates, a three-dimensional blueprint made of pure gravity. They were the universe's hidden framework. Only later, after the cosmic fog cleared, could the ordinary gas feel this structure. The hydrogen and helium began to flow. Drawn by gravity, it streamed into those waiting dark matter wells. The gas swirled and heated and eventually ignited into the first stars and galaxies. But it did so within a preordained architecture. The luminous universe we see is just the decoration on this invisible scaffolding. The glittering cities built along ancient, unseen river valleys. Without this dark framework, the cosmos would still be a formless, expanding haze. The story of structure is the story of dark matter drawing the map long before light could fill it in. The invisible framework was in place, but the real drama was just starting. For hundreds of millions of years, those density ripples grew slowly. The universe was still expanding fast, pulling everything apart. And the overdensities were so slight that gravity's pull was gentle. Growth was linear. If a region was 1% denser than average, it would become 2% denser over a certain time. A predictable, proportional increase, like a gentle swell on a vast ocean, slowly rising. But gravity isn't a patient force forever. It's an amplifier. As these regions steadily gathered more matter, their density advantage grew. They weren't just slightly denser patches anymore. They became pronounced hills on the cosmic landscape. And then they crossed a critical threshold. The era of linear growth ended. The universe entered the nonlinear regime. Here, everything changed. The rules of simple addition no longer applied. In these now significant lumps, gravity's pull became overwhelmingly strong, not just on their surroundings but on themselves. They began to collapse under their own weight. This is a runaway process. The collapse makes the region denser, which increases gravity, which accelerates the collapse. It becomes a self-feeding loop. Crucially, these regions became so bound by their own gravity that they could decouple from the overall expansion of the universe. While space continued to stretch on the grand scale, these knots of matter stopped expanding. They effectively went their own way, turning inward and beginning to condense. This was the pivotal transformation. The smooth, wave-like ripples imprinted at the beginning of time were now breaking. They were crystallizing into distinct, separate entities. These were the first true protostructures. Not just statistical variations, but real, collapsing lumps of dark matter and gas. They were the direct progenitors, the embryos of the first galaxies. And where these collapsing regions intersected, where the filaments of the growing cosmic web met, the seeds for something even grander were planted. These intersections would become the future sites of immense galaxy clusters. The largest gravitationally bound structures in existence. The universe was no longer a subtle tapestry of variations. It was becoming a collection of places. Those dark matter knots weren't just seeds. They were the first real nurseries. Inside them, it stops being just about gravity. The gas is there, hydrogen, helium, but it's hot, it's turbulent. To get a star, that gas has to cool. It has to settle, and in the early universe that's hard. The only way for the gas to lose heat is to radiate it away. When hydrogen atoms collide, they give off a faint ultraviolet glow. That faint cooling is enough. Over millions of years inside a halo, pockets of gas start to chill. They contract, they break into dense clouds, and in those clouds, gravity takes over one last time. It pulls the gas inward until the core gets so hot, so dense, that nuclear fusion ignites. The first stars are born, and these stars, they were something else. Astronomers call them Population 3, nothing like what we see now, made from pure hydrogen and helium. No heavier elements to help them cool, so they grow huge. Not 10 times the sun's mass, 100 times, maybe more, cosmic behemoths. Their lives are furious. They burn fuel at a prodigious rate. They shine with a harsh ultraviolet light. A single one could outshine an entire modern galaxy, but that brilliance has a cost. A star that massive lives fast. It dies young, not billions of years. Millions a flash in the pan, but in that short life it changes everything. Its intense radiation blasts into the surrounding gas. This isn't gentle starlight. It's an ionizing torrent, powerful enough to strip electrons from hydrogen atoms across vast distances. That process is called reionization. It starts to reheat the cosmic gas. It changes its state, like turning on floodlights in a dark, foggy room. The universe is being transformed from a neutral fog back into a transparent, ionized plasma. But the star's final act is even bigger. At the end, it doesn't fade, it detonates, a supernova of unimaginable power. In that explosion, the star's furnace forges the first heavy elements. Carbon, oxygen, silicon, iron, created in an instant and blasted into the void. The universe's first act of stellar alchemy. Before this, the cosmos is chemically simple. Hydrogen, helium, a trace of lithium. After, it's seeded with the raw materials for everything to come. Rocks, water, organic molecules, planets, life. So these first proto-galaxies aren't just collections of stars. They're the first chemical factories. Their brilliant, short-lived stars write the opening chapter of cosmic complexity. The heavy elements they create don't disappear. They pollute the surrounding gas. When the next generation of stars forms, it forms from this enriched material. That makes them different, smaller, longer-lived, capable of forming planetary systems. The legacy of those first monstrous stars is inside you. Every atom of oxygen you breathe. Every bit of carbon in your body forged in a star, and the very first of those stars were born in those faint, collapsing ripples from the dawn of time. But this is only the beginning of assembly. How did these first, isolated stellar factories find each other? The first galaxies were born. They were lonely. Fragile, held in their small dark matter halos, drifting through a mostly empty cosmos. But gravity was still working. It wasn't just pulling gas inward. It was pulling the halos themselves toward each other. The blueprint becomes a living structure. The universe builds from the bottom up. Picture a dark ocean. Small islands of matter form. They aren't static. Each island has its own gravitational pull, a tiny dip in space. Over immense time, islands that are close feel that mutual tug. They start a slow drift toward one another. That's the hierarchical merger model, the universe's primary method. Small things merge to make medium things. Medium things merge to make large things. Think of it like cosmic bumper cars, played out over billions of years. Two small proto-galaxies would draw together. They wouldn't crash in a fiery explosion. Space is too vast, stars are too small. Instead, their dark matter halos would overlap, intertwine. The two structures would swing past each other, gravity weaving them into a tangled dance. They might orbit for eons, losing energy until they coalesce. They become one. A new, larger galaxy is born. This process repeats constantly. That new, larger galaxy has a stronger gravitational reach. It becomes a bigger target. It attracts other, smaller halos. It consumes them. Astronomers call this galactic cannibalism. A larger galaxy absorbs a smaller one, swallows its stars, its gas, its dark matter, adds them to its own bulk, and it doesn't stop. These medium-sized galaxies are drawn together by the larger-scale pull of the cosmic web. They stream along invisible filaments of dark matter, funneling toward the densest intersections. Where these rivers meet, you get the true titans, galaxy clusters. Hundreds, thousands of galaxies, bound in a single immense gravitational well. The largest structures, all built from the bottom up, an endless chain of mergers that began with those first tiny halos. The history of this assembly is written in the stars. When a large galaxy absorbs a smaller one, it doesn't digest it perfectly. The stars from the victim are strewn out. They form faint streams and shells, a stellar halo. If you could map the motions of millions of stars in the halo, you'd find distinct families, groups moving together. They all came from the same dwarf galaxy consumed billions of years ago. Our galaxy's halo is a graveyard of its past meals, a fossil record. Even the small satellite galaxies orbiting the Milky Way, like the Magellanic Clouds, are likely not permanent. They are the next courses. The universe is still building itself, one merger at a time. The assembly didn't just make islands, it made a kind of tapestry. So the universe at the largest scale, it's not just galaxies scattered around. It's a network, a web, and the structure is actually very simple. There are 3 parts. You have the dense knots, the nodes. Those are the galaxy clusters, these huge cities of thousands of galaxies. Then you have the threads that connect them. Those are the filaments, long, thin rivers of galaxies and gas, stretching for hundreds of millions of light years. And then between the threads and knots, you get the voids. Huge spherical areas of almost nothing. They can be hundreds of millions of light years across, with maybe just a few galaxies inside. The universe ends up looking like a sponge. Or like the neural network of some kind of brain, and that's not an accident. It's the direct result of gravity acting on those original ripples. You remember that baby picture, the cosmic microwave background? That blotchy map of warm and cool spots. The warmest spots, the densest seeds, they collapsed first and fastest. They became the superclusters, the rich clusters, the nodes of the Webb. The moderate ridges, the areas that were just slightly above average, they got pulled towards several neighboring peaks. They didn't collapse into one point. They got stretched, they became the bridges between the dense knots. Those are the filaments, and the coolest spots, the underdense regions. Gravity was weaker there. Matter was actually flowing out of them toward the denser areas. They got left behind. As the universe expanded, these underdense regions expanded even faster, emptying out more. They became the great cosmic voids, so the Webb is like a frozen moment in a dynamic process. It's a snapshot of gravitational flow. All the matter in the filaments is still moving, streaming slowly toward the nodes. The Webb isn't static architecture. It's a map of rivers all flowing toward the deepest lakes. When astronomers make 3D maps of millions of galaxies, this Webb just appears in the data. It's not a model we put on it. It's the structure we actually see. Galaxies line up along these delicate filaments like dew on a spider's web. They gather in sparkling clusters at the intersections. And between them, you find these staggering deserts of space. The voids are so empty that if our Milky Way were in the center of one, we might not have seen another galaxy until the 1900s. Our night sky would be profoundly dark. This architecture defines everything about the universe's large-scale structure. It tells us the initial conditions, those quantum whispers. They had the blueprint for this whole sponge-like geometry. The pattern was written at the beginning. Gravity was just the artist tracing the lines for billions of years. So when you look at a simulation of the cosmic web with its delicate filaments and gaping voids, you're not looking at a computer's imagination. You're looking at a prediction of that first light, all grown up. You're seeing the ultimate fate of a ripple. We can't rerun the universe. We can't watch it all happen again. So how do we test a story that goes from the first particles to galaxies? The answer is in computers, some of the most powerful ones we have. Cosmologists build universes inside them. These are digital labs. The only rules are the laws of physics. They're called cosmological simulations, things like the Millennium Run, Illustris TNG. They start with a box, a digital box representing a huge piece of space. They put in the starting conditions, a smooth sea of virtual particles. and they imprint it with the exact pattern of tiny ripples. The same ones we see in the cosmic microwave background. Then they program in all the physics we know, gravity's pull, the complex flow of heated, swirling gas. The recipes for making stars, the explosions from supernova, they put in dark matter, they put in dark energy, then they press play. The simulation calculates the dance of trillions of particles. It watches dark matter clump into halos. It sees gas flow in, cool down, and ignite. The first virtual stars. It sees galaxies merge. It sees them grow. It runs for billions of cosmic years, compressed into months of supercomputer time, and when it's done, they have something, a time-lapse movie of the cosmos. A full, digital universe. They can step inside it. They can point a virtual telescope. They can count the galaxies, measure their shapes and colors, map where they are. They can trace the filaments of the cosmic web, see the vast, empty voids, and then they compare it. They compare this digital cosmos to our real maps of the sky. And the match is breathtaking. The simulated universe looks real. It has the same large-scale structure, that sponge-like shape. It has galaxies with the right sizes. In the right places, with the right number of stars, it makes realistic spirals, realistic ellipticals. This agreement means something. It means our basic understanding is correct. The gravity, the initial conditions, the dark matter, the simulation validates the whole story, from the first ripple to the web we see now. But it's more than just confirmation. It's a time machine. Scientists can rewind it. They can follow a single galaxy backward, see which smaller galaxies merge to build it. They can find the exact dark matter halo that seeded a massive cluster. They can watch the cosmic web being woven, thread by thread. They can also run experiments. What if dark matter was different, warmer, more interactive? Run the simulation again, see if the galaxies match reality. What if dark energy changed strength over time? The simulation can test that. These digital universes let us ask, what if? In a way observation never could. They show the interplay of forces, how a supernova explosion can blow gas out of a small galaxy, stifle its growth. How the merger process shapes a galaxy's destiny. The simulation shows it in dynamic detail, so when you see a visualization of the cosmic web, filaments and clusters shimmering. Remember, that's not just an artist's idea. It's a snapshot from a universe born from equations, a universe that grew over billions of simulated years. From the same quiet hum that started our own, it's perhaps our most powerful evidence that we're reading the cosmic story right. We haven't just pieced the past together from fossils. We've learned the rules well enough to grow a new cosmos from scratch, and it looks like home. Those digital universes show us where it all ends up, the final thing that gets built. A galaxy cluster. To really see the scale of what gravity makes, you have to look at one of these things directly. And a galaxy cluster isn't just a bunch of galaxies near each other. It's one single thing bound together by gravity, the biggest structure in the cosmos that holds itself together. You could think of it as a continent where the galaxies are like cities. Inside it, hundreds, even thousands of galaxies orbit a common center. Not just spirals, but these giant elliptical galaxies, smooth ones, often right at the cluster's heart. But the galaxies are just the part you can see. For every bit of starlight, there's far more in the form of this incredibly hot, thin gas. It fills all the space between the galaxies. This intracluster gas is heated to tens of millions of degrees, so hot it glows in X-rays, not visible light. So from where we are, a massive cluster is this brilliant, diffuse X-ray source. A glowing cloud of plasma held in the cluster's deep gravity well, and then, making up most of the mass, over 80%, is the dark matter halo. An invisible scaffold that everything else sits inside. The numbers are hard to grasp. A typical large cluster is millions of light years across. You could line up thousands of Milky Ways across one. Its total mass can be a quadrillion times the Sun's mass, a 1 with 15 zeros, all of it bound together, moving as one system. We know some of the nearby ones by name. The Virgo cluster, our nearest large neighbor with over 1,000 galaxies. The Coma cluster farther out, a perfect example of a rich, dense cluster. A spherical swarm of galaxies. These are the endpoints, the ultimate cities in the cosmic web, and when we study them, we're not just cataloging enormous things. We're looking at the final result of the universe's only growth process. Every property of a cluster, its size, its shape, how many galaxies, how hot the gas is, comes directly from those initial conditions and the relentless work of gravity. It's like finding a vast, ancient city, and from its layout and architecture, deducing the geography it was built on and the rules that guided its growth. The cluster holds the entire history of cosmic structure, frozen in its present state. Decoding it is reading the final chapter of the story that started with a whisper. The real center of a galaxy cluster isn't the galaxies, it's what's between them. That huge space, millions of light years across, looks like nothing in a regular telescope. But it's not empty, it's filled with something. Astronomers have a name for it, the intracluster medium, and it's not cold, it's a plasma, a thin, hot gas. So hot it glows in X-rays. The temperature is enormous, tens of millions of degrees. You'd only find that kind of heat on Earth inside a nuclear blast. That heat comes from gravity, from the pull. Over billions of years, all the dark matter and gas and galaxies fell in. They gained speed. They crashed into the gas that was already there. Moving thousands of kilometers every second, all that motion, that energy turned into heat. It's the cluster's own gravity, turned into a kind of fire that fills everything. This intracluster medium has a secret. If you weighed it, you'd find it holds more normal matter, more atoms than all the stars in all the galaxies put together. The galaxies, the stars, they're just the bright pieces, the decoration. Most of the universe's ordinary material is here, in this hot, shapeless fog. And because it's so hot, it shines in X-rays. So when telescopes like Chandra look at a cluster in X-rays, they don't see the galaxies. They see a huge, soft glow. A luminous cloud that shows the cluster's true shape, its true mass, better than starlight ever could. This hot gas is more than just a leftover, it's a record. A fossil. By studying it, scientists can read the cluster's history. They map its temperature. A smooth, even hot region means a quiet cluster, one that formed long ago and settled. But many clusters show a lopsided X-ray glow, or they have shock waves in the gas, like sonic booms but cosmic. Those are scars from mergers when two clusters collide, which takes hundreds of millions of years. Their intracluster mediums smash together. They create huge pressure fronts, turbulence, all visible in the X-rays. It's like tree rings, but the rings tell the story of a crash. And there's another clue in this plasma. Its chemical fingerprint. This gas isn't just hydrogen and helium. Spectroscopy shows heavier elements, iron, oxygen, silicon, neon. Those elements weren't made in the space between galaxies. They were forged in stars, inside the cluster's galaxies, then blown out into the void by supernova. Over billions of years, stellar winds and explosions from countless generations have polluted this space. So when we analyze the hot gas, we're sampling the whole history of the cluster, all its star formation, all its stellar deaths. The intracluster medium is the cluster's memory. A vast hot archive. It holds the story of its violent assembly and the chemical legacy of every star that ever lived inside it. It shows that the space between things is never really empty. Often, that's where the important story is written, in a language of extreme heat and ancient light. The most direct proof of the cluster's hidden mass isn't its glow. It's what it does to light. The weight of a galaxy cluster is so immense it bends spacetime. It creates a gravitational lens. That was one of Einstein's predictions. Light from a galaxy billions of light years behind the cluster. It doesn't travel straight through that warped space. Its path curves. The cluster acts like a flawed magnifying glass. A natural telescope. When Hubble looks at a massive cluster, you often see something strange around the edges, stretched arcs of light, like the background sky was smudged. Those aren't features of the cluster. They're distorted, magnified images of galaxies far behind it. Sometimes the same background galaxy appears multiple times. As faint, mirrored images in a ring around the cluster's core, a gravitational mirage. It shows mass-curved space, but it's more than a curiosity. It's a tool. A scale. By measuring the shape of these distortions, astronomers can map the warped space. From that map, they can calculate the total mass bending the light. The total mass of the cluster, and the result is always the same. The mass from lensing is far greater than the mass from all the visible stars and hot gas. There's a huge amount of missing mass, invisible mass, holding the structure together. This is the most direct evidence for dark matter. It's not inferred from galaxy rotation. It's not theory, it's a measurement. We see the light bending. The only thing that bends light that much is mass. Mass we can't see. The lensing map shows where that mass is. It traces the dark matter halo, the invisible scaffold. It shows the dark matter is a smooth, massive cloud filling the entire cluster, with the galaxies just embedded in it. Like fireflies in amber, so those beautiful arcs of light around a cluster in a Hubble image. It's more than a pretty picture. You're looking at a map of the invisible. A direct imprint of dark matter's grip. It's the final piece. It explains how those first tiny ripples grew into the titans we see. These clusters are still forming. They're still growing, and they grow through the most violent events we know of in the modern universe. When two galaxy clusters collide, it's the final stage of that assembly. The merging of continents, the energy is staggering. The only thing more energetic was the Big Bang itself. You have two structures, each with the mass of a quadrillion suns, moving at thousands of kilometers per second. They don't just pass through, they plow together. The galaxies inside them are so far apart they mostly slip past, like ghosts, but the space between them isn't empty. It's filled with that hot gas, that 100 million degree plasma, and when these two seas of plasma meet, they can't avoid a collision. They slam together. The result is a cosmic tsunami. A shock wave rips through the gas, heating it even more. It creates these vast, curved fronts of energy. In X-ray telescopes, you see them as brilliant edges in the cloud. The largest shock waves in the known cosmos. For scale, the shock front in the Bullet cluster is about 2 million light-years across. You could put our entire local group of galaxies inside it. With room to spare, the violence is almost beyond comprehension, but we can see it, we can map it, and in these collisions, something profound happens. The different parts of the cluster get separated. The dark matter, which only feels gravity, passes right through the chaos, unaffected. The galaxies, mostly empty space, they do the same. But the hot gas made of normal particles gets caught. It slows down, it piles up. So after the merger, you get a signature. The bulk of the mass mapped by gravitational lensing is in one place. The hot gas glowing in X-rays is in another. They've been wrenched apart. The Bullet cluster shows this perfectly. It's like seeing two clouds of smoke pass through each other, while the bits of metal inside keep going. That separation is direct proof that most of the mass is something that doesn't interact like normal matter. It's a fingerprint of dark matter. Caught in the act, these mergers are more than just cosmic wreckage. They are our ultimate laboratories. We can't create conditions of this scale and energy anywhere. But the universe does it for us. By studying the shock waves, we test plasma physics under extremes we could never replicate. By mapping the separation of mass from gas, we test the nature of dark matter. Does it truly only feel gravity? These collisions tell us yes. They even let us probe the strength of gravity itself. On the largest scales, every major merger is a natural experiment. A chance to see if our laws of physics hold up in the most energetic arena imaginable. And they show us the cosmic web isn't a static monument. It's a dynamic, living structure. The great nodes are still coming together, drawn by the same gravitational threads that have been pulling for billions of years. The universe is still building its largest cities. One catastrophic merger at a time. Even as clusters merge, there's something else happening, a larger force working in the background. Gravity has a rival. For the last several billion years, the universe hasn't just kept expanding. That expansion has started to accelerate. Something is pushing space apart faster and faster. We call that something dark energy, and when it emerges, it changes the whole cosmic game. Gravity pulls matter together to build structure. Dark energy does the opposite. It stretches the fabric of space, it pushes things apart. In the early, dense cosmos, dark energy's effect was tiny, negligible. Gravity ruled, but as the universe expanded, as it thinned out, dark energy's constant push began to outweigh gravity's pull. Gravity's pull was weakening, and dark energy became the dominant force, the force shaping cosmic destiny. That shift puts a brake on the growth of the largest structures. You can think of dark energy as a kind of cosmic pressure. It makes the space between galaxy clusters grow faster, ever faster. It doesn't destroy what's already built. The clusters, the filaments we see, they're already bound by gravity. They hold together, but dark energy makes it much harder for new, vast structures to form. It's like trying to build a sandcastle as the tide comes in, but the tide is the space between the grains of sand, relentlessly rising. Matter that might have once fallen into a growing filament now finds the distance to its neighbors increasing too fast. Increasing too rapidly, the gravitational handshake can't be completed, not across that widening gulf, so the era of building the grand cosmic web, that era is largely over. The architecture we see is essentially complete. The future will be one of separation, not assembly. The great nodes of the web will drift apart. They'll become isolated islands. Islands in an ever-darkening sea of expanding space. This tension between gravity's ancient, patient pull and dark energy's new, relentless push, that tension now writes the final chapters. The final chapters of our universe's story. It determines not just the fate of galaxies, it determines the ultimate destiny of all structure. That story, from quantum whispers to colliding clusters, is a powerful one. But it's a scientific model, and a model needs evidence. The path from prediction to confirmed science has these milestones. The first major piece was that baby picture, the cosmic microwave background. For decades, it looked perfectly smooth, just a uniform glow. Then in 1992, a satellite called COBE, the Cosmic Background Explorer, changed that. It didn't just see the glow. It measured the temperature with precision, and it found the variations, tiny anisotropies, fluctuations of just a few millionths of a degree. They presented a map. A blotchy, mottled sky. It was the first clear image of the primordial ripples, the seeds of all structure imprinted in light. That discovery confirmed a core prediction. The universe's blueprint was real, and we had the technology to read it, but a blueprint isn't a building. The next step was to map the building itself. To see if the grown-up universe matched that infant photo, that required a different kind of telescope. Enter the Sloan Digital Sky Survey. Starting in 2000, it began mapping the night sky. Not just pictures, but using spectroscopy to measure distances to millions of galaxies. For the first time, we weren't looking at a flat sky. We were building a three-dimensional atlas. The result was breathtaking. When they plotted the positions of those millions of galaxies, the structure emerged, not a random scatter, a vast, delicate network. Filaments and walls of galaxies, immense clusters at the intersections, and giant, echoing voids in between. The cosmic web revealed in detail. It was no longer just theory or simulation. It was an observed fact. The universe at its largest scale is a sponge, a web, and then came the link. Statisticians compared this 3D map of the modern web to the 2D map of the ancient microwave background. They asked if the densest clusters and filaments we see today line up statistically with the warmest spots on that baby picture. The answer was yes. The correlation was strong. The slightly overdense regions in the early universe are, with remarkable fidelity, the locations of the richest galaxy clusters today. The slightly underdense regions became the great voids. This was the final statistical confirmation. It closed the loop. The initial fluctuations in the first light are the direct ancestors of the large-scale structure we inhabit. Every observation, from that first whisper of anisotropy to the grand architecture of the web, has been a piece of evidence. Together, they form a coherent, tested model. A standard model of cosmology. It tells us how everything, from the tiniest ripple to the largest cluster, is connected in one continuous story. Even this grand picture isn't the final word. Inflation works incredibly well, but it's not the only idea. Cosmology is alive, and the story of those first ripples has open questions. Some researchers look for origins without rapid inflation. Bouncing universe models, for example, a cosmos that contracts and then rebounds, with quantum effects from the bounce seeding the density variations. Others draw from string theory, string gas cosmology. It suggests the early universe was a hot, tangled web of fundamental strings, and their vibrations created the initial patterns. These aren't mainstream yet, but they represent a vital process testing the boundaries of our best theories. Even within the established framework, precise measurements show subtle tensions. One of the most significant is the Hubble tension. It's a disagreement about how fast the universe is expanding right now. We have two main ways to measure this expansion rate, the Hubble constant. One method looks at the early universe at the cosmic microwave background and works forward using our standard model. The other method looks at nearby objects. Pulsating stars, supernova, it measures their distances and speeds directly. These two methods should give the same number, but they don't. They disagree by a small, persistent amount. A discrepancy that's withstood over a decade of better observations. This isn't a crisis, it's a clue that something in our model might be incomplete. Maybe dark energy changes over time. Maybe neutrinos have unexpected properties, or a new, undiscovered particle or force played a role early on. The Hubble tension reminds us our map of cosmic history, though detailed, may have blank spots. Or a wrong turn we haven't noticed. Furthermore, the cosmic microwave background itself, that pristine baby picture, shows faint anomalies, large-scale patterns that seem slightly off. A mysterious cold spot, a curious alignment of fluctuations sometimes called the axis of evil. Most scientists think these are likely statistical flukes. The universe's natural randomness, but they could be hints of physics beyond our current understanding, a signature of something before inflation, or a trace of our universe interacting with another. These puzzles aren't failures, they're the frontiers. They tell us the story of cosmic structure, from quantum whisper to galactic city, is still being written. Our current model is a masterpiece of human deduction. It connects the first instant to now with stunning accuracy. Yet the universe, in its infinite complexity, always holds a few more cards close. The search for a complete understanding continues, driven by the same curiosity that made us look up and wonder how those tiny ripples could ever become everything we see. We live inside the Milky Way, a spiral galaxy, hundreds of billions of stars, but it's not alone. It's part of a small family, a local group, a few dozen galaxies. And our nearest large neighbor, Andromeda, is slowly coming toward us, a merger billions of years from now. This local group, though, it's not a major center. It's a small outpost. We're part of something much larger, something almost invisible from where we are. Our local group is being pulled. It's in a slow, cosmic river. We're on the edge of a titanic structure, the Laniakea supercluster. Laniakea means immense heaven, and it is. This supercluster isn't a dense knot, it's a vast filament. A river of galaxy groups, hundreds of millions of light years long, all flowing toward a common center of gravity, a region called the Great Attractor. The Milky Way is like a single leaf, caught in a gentle current on the surface of this immense, slow stream. So when we look at the night sky, we're not seeing a random scattering. We're looking at our local neighborhood within a specific filament of the cosmic web. The stars we see are our galactic home. The faint, fuzzy patches, those are other galaxies. Our nearby relatives in the local group, and the great, dark spaces between them, they trace the outlines of the larger flow, the flow we're part of. That perspective shifts everything. We're not just looking at the universe, we're situated inside its specific architecture. Our address isn't just solar system, Milky Way. It's solar system, Orion Arm, Milky Way galaxy, local group, Laniakea supercluster, universe. Every part of that address comes from those first ripples. But the connection is more intimate. Look at your hand. The hydrogen atoms in your body's water, they're primordial, made in the first few minutes after the Big Bang. Every other atom was forged later. Carbon, oxygen, nitrogen, iron. These heavier elements were cooked in stars, in nuclear furnaces, stars that formed because of those initial density variations. Stars that lived and died and exploded. They seeded their galaxies with the raw materials for planets and for life, the calcium in your bones, the oxygen you breathe. The iron in your blood, all of it was stardust, created in generations of stars, and the existence of those stars traces back to a specific, slightly warmer spot on the cosmic microwave background. We're not just observers of this story, we're a chapter in it. Our bodies are made of atoms from that great construction project. We are the universe literally becoming aware of itself. So to understand that journey from quantum whisper to galaxy cluster is to understand part of our own origin. It connects the vastness of space and time to the chemistry of life. It tells us the same physical processes that sculpted the largest structures also assembled the pieces that make us. In learning how the cosmos built its grandest cities, we learn, in a physical way, where we came from. The final frontier in this story is opening now. The next chapter of cosmic structure isn't written in ancient light. It's in the data streams from new observatories. Machines built to ask the next questions, to see the invisible clearly. At the forefront is the James Webb Space Telescope. Its main job is to look back into the cosmic dawn, to catch the light of the very first galaxies as they turn on. But it's doing more than spotting them. It's showing us these infant galaxies not as isolated points, but as they were, embedded in the early filaments of the cosmic web. Webb can see the faint glow of hydrogen gas lit by those first stars. It traces the delicate scaffolding where matter flowed. We're watching, across billions of years, how those primordial ripples first gathered material. How the web began to light up. But to understand the full architecture, we need a map of the present-day universe, a map of unmatched scale and precision. That's the goal of two monumental projects, the Euclid Space Telescope from the European Space Agency and the Vera C. Rubin Observatory, a ground-based telescope being built in Chile. Their missions are complementary and colossal. Euclid will orbit and survey a third of the sky. In both optical and near-infrared light, it will measure the shapes and positions of over 1 billion galaxies. The Vera C. Rubin Observatory, with its enormous mirror and camera, will image the entire visible sky every few nights for a decade, creating an unprecedented motion picture of the cosmos. What will these surveys do? They will map the dark universe by measuring the subtle distortions in the shapes of billions of galaxies. Weak gravitational lensing, they'll create the most detailed three-dimensional chart of dark matter ever made. We'll see its distribution, its filaments and halos, with a clarity that simulations can only dream of, and by pinpointing the distances to tens of millions of galaxies, these telescopes will measure the expansion history of the universe. With razor-sharp accuracy, they will test the nature of dark energy. Is it a constant force like Einstein's cosmological constant, or does its strength change over time? The data will tell us. These instruments are forensic tools for the cosmos. They'll trace the growth of structure from the early Webb seen by Webb to the modern Webb around us. They'll measure how gravity has pulled matter together over billions of years, and by comparing this measured growth to the predictions of our standard model, they'll perform the ultimate stress test. Any deviation, any mismatch between the observed structure and the predicted structure could be a crack in our understanding, a sign of new physics. Maybe a modification to Einstein's theory of gravity on the largest scales, or a new property of dark matter or dark energy. The goal isn't just to confirm our story. It's to find the places where the story is incomplete, where the universe still has secrets to tell. 13.8 billion years. It's a number, but it's not something you can really hold in your mind. It's too big, it becomes an abstraction. The whole story, from the first quantum ripples to the great clusters we see now, it all happens across that span. To even begin to feel it, you have to shrink it down, compress the whole history of the cosmos into a single year, a cosmic year. So at the very first instant, midnight on January 1st, that's the Big Bang. Those quantum ripples, they're imprinted almost immediately. The cosmic microwave background, that first light, it's released just days later. The first stars, the population 3 stars, they flicker on in early January. They live fast and die, and they seed space with the first heavy elements. Our own galaxy, the Milky Way, it starts to come together around March. It's a slow gathering. Gas and smaller fragments, and the months go by. The cosmic web weaves itself. Galaxy clusters form where the filaments cross. Our own solar system, with the sun and its disk of dust, it doesn't even condense until early September. Life on Earth emerges in late September, maybe early October. The dinosaurs, their whole reign, that's in mid-December. And all of recorded human history, from the first cities to now, to the Webb telescope, all of that fits into the last 10 seconds. The last 10 seconds before midnight on December 31st. Every story, every person, all of it in that final moment. That scale, it changes how you see gravity. It shows you its true nature. It's not a force of sudden action. It's a force of immense patience. For billions of those real years, gravity just whispered. A gentle, persistent tug on atoms, on dark matter. It worked in the background across epochs, compounding tiny, tiny advantages. Turning a faint density ripple into a protogalaxy took hundreds of millions of years. Growing that into a massive cluster took billions more. There was no rush. The universe had all the time in the world. So when we look at a galaxy cluster today, we're not looking at a finished product. We're seeing a snapshot, a moment in a process that's still going, but we are seeing the result of the most patient construction project you could imagine. Every filament of the cosmic web, every glittering city of galaxies, it's the accumulated work, countless cosmic years of work, a testament to a simple force given near infinite time to sculpt the void. And it makes our moment here, in the last seconds of the cosmic year, it doesn't make it insignificant. It makes it a remarkable point of awareness, a moment where the universe, through us, can look back and begin to understand its own story. There's this deep resonance, almost haunting, between our scientific story and humanity's oldest tales. For thousands of years across every continent, people looked up at the stars and told stories about how it all began. In ancient Egypt, the god Atum emerged from a dark, endless ocean called Nun, bringing order. The Norse myths spoke of Ginnungagap, a yawning void between fire and ice where life first stirred. Hindu cosmology describes the universe cycling through periods of creation and dissolution, emerging from a cosmic egg. The common thread is profound. A structured, living cosmos coming out of a state of primordial chaos or nothingness. Our modern scientific narrative, with its inflationary vacuum and quantum ripples, isn't a rejection of those ancient intuitions. It's their continuation. It's the same fundamental human question, where did we come from, asked with new tools. The language has changed from gods and serpents to quantum fields and general relativity. The evidence has shifted from oral tradition to the precise data from satellites and telescopes, but the core awe remains, the recognition that we are part of something that had a beginning, that transformed from simplicity into breathtaking complexity. This connection is more than poetic. It shows a fundamental pattern in how humans understand existence. We are pattern-seeking creatures. We observe the structured world around us, the cycles of day and night, the seasons, the predictable motion of stars, and we instinctively ask how that order was established. Every creation myth is an attempt to answer that, to bridge the gap between the chaotic unknown and the familiar, ordered world we live in. Our scientific model does the same thing. It starts with a hot, dense, nearly uniform state, a kind of cosmic chaos, and meticulously explains, step by step, how the laws of physics drew forth galaxies, stars, and planets from that initial formlessness. The difference, of course, is testability. A myth is a cultural truth, a story that binds a people together and explains their place in the world. A scientific theory makes specific, quantitative predictions that can be confirmed or refuted by observation. We didn't accept the inflationary Big Bang model because it felt intuitively right. We accepted it because its predictions, the specific pattern of ripples in the cosmic microwave background, the abundance of light elements, the existence of large-scale structure, matched what we saw in the sky with stunning precision. It's a story that invites and withstands relentless scrutiny, and yet placing our cosmology within this long human tradition is humbling. It reminds us that our current understanding, however detailed and evidence-based, is still a chapter. Not the final word. The scientists running simulations and analyzing data from the James Webb Telescope are engaged in the same essential quest as the storytellers who gathered around ancient fires. They are mapping the unknown. They are constructing a narrative of origins that makes sense of the world they see. Our narrative is powerful because it is constrained by evidence, but it is driven by the same timeless wonder. We are still telling the story of how order came from chaos. We're just using a new, incredibly precise vocabulary, written in the language of mathematics and written across the sky itself. You've got this loaf of raisin bread baking. The dough is space, the raisins are galaxies, and as it bakes, the dough rises, it expands, so every raisin moves away from every other one. That's the expansion of the universe. But if a few raisins started out just a little closer together, that small grouping stays. It's preserved. Actually, it's amplified as the bread rises. They stay relatively closer, they form a clump, and then there's the yeast. The yeast works locally. It puffs up the dough around those clustered raisins. That yeast is gravity. It causes local clumping inside the overall expansion. So two things are happening. The whole loaf is getting bigger, pushing everything apart. But locally, gravity is pulling matter into denser knots. That's the cosmos. The overall expansion carries galaxies apart. But those initial tiny overdensities, they were the raisins that started slightly closer. And gravity, over billions of years, pulled matter into those spots, creating the clusters and filaments we see, even as the cosmic dough keeps rising. The legacy of a galaxy cluster is in its chemistry, not the light but what's in the gas, that hot plasma between the galaxies. It's more than hydrogen and helium. It's a soup: oxygen, carbon, iron, silicon, the ashes of stars. They were made inside stars, inside the galaxies that orbit the cluster. When those stars died, many exploded. Supernova, those explosions did something. They acted like bellows. They blew the new elements out of their galaxies, into the space between. Over billions of years, stellar winds added to it. More pollution, the cluster's gravity trapped it, held it there, so the hot gas becomes a reservoir, a mixed archive of everything every star in every galaxy ever made. We can read it with X-ray spectroscopy. The hot gas emits X-rays, not a smooth glow. It has dips and peaks, a fingerprint. Each element at those temperatures emits light at precise energies. Iron has a signature, oxygen has another. With an observatory like Chandra, astronomers can measure it, the temperature, the exact composition, how much iron is there compared to oxygen or silicon. It's chemical archaeology on a huge scale. What it tells us is the star formation history of the whole cluster. The relative amounts of elements are a clock. A recipe: iron comes mainly from white dwarf explosions, a slower process. Oxygen and magnesium come from massive stars. They live fast and die young. The ratio of iron to oxygen tells you about the pace, the timing, across the cluster's history. A cluster with a lot of iron means its galaxies had a long era of stellar birth and death, building up elements patiently. This fingerprint is a sum total. It smooths out thousands of individual galaxy stories into one narrative of the cluster's evolution, and it has a consequence for the cosmos. These enriched elements don't stay locked in the cluster forever. During violent mergers, some of this gas gets ejected into the wider intergalactic medium. It seeds the filaments of the cosmic web with the raw materials for complexity. Wherever new galaxies form later, they'll condense from gas already sprinkled with these heavy elements. That includes the ingredients for rocky planets, for oceans, for the chemistry of life. So studying a cluster's chemistry traces more than stellar history. It shows how the universe, over billions of years, got seeded, with the building blocks that make worlds like ours possible, the iron in our blood, the oxygen in our air. It began in stars, and much of it was mixed and distributed on the scale of these gravitational titans. There's this faint echo buried in the cosmic web, a kind of whisper from the universe's early, fiery stage. Not a sound you could hear, but a pattern we can measure, frozen into where galaxies are. Scientists call it Baryon acoustic oscillations. It's one of our most precise cosmic measuring tools. To get it, you go back before the first light, a hot, dense plasma, so packed that light and matter were glued together. In that searing soup, gravity was always pulling matter into tiny overdensities, the seeds of future structure, but there was a counterforce, immense pressure from the intense radiation. It pushed back, so you had this tug of war. Gravity pulls a clump inward, radiation pressure blasts it back outward. That back and forth set up waves. Pressure waves rippling through the plasma like sound waves in air. They were literal sound waves crossing the early universe. These waves traveled outward from every overdense seed, creating expanding spherical shells of slightly denser matter, like ripples from a stone in a pond. But there was a cosmic deadline, when the universe cooled enough to become transparent. When atoms formed and the cosmic microwave background was released, that hot plasma vanished, the music stopped, the sound waves froze in place, their furthest reach was etched into the cosmos. It left a specific, preferred scale imprinted, a spherical shell of matter with a radius of about 500 million light-years, a fossilized echo of that early cosmic sound. Now fast forward billions of years, where are those spherical shells? They expanded with the universe, grew to a colossal size, and they guided where galaxies would eventually form. Galaxies were more likely to condense on these vast, fossilized shells, so when we make a 3D map of millions of galaxies today, we should see a subtle statistical preference. A tendency for galaxies to be separated by this specific, enormous distance. Not every pair is exactly that far apart, but when you average over millions of them, this preferred scale emerges from the noise. A faint, ghostly imprint of an ancient sound wave. That imprint is the Baryon acoustic oscillation scale, and it acts as a cosmic ruler, a standard ruler of known length stamped across the sky. By measuring the apparent size of this ruler at different distances, which means at different times in cosmic history, we can measure how the universe has stretched over billions of years. It's like a ruler made of a material that expanded with space itself. By seeing how long the ruler looks to us now, compared to its known original length, we can calculate the expansion rate of the universe at the time that light was emitted. That gives us a direct, precise history of cosmic expansion. It's a powerful, independent way to probe dark energy. By seeing how the expansion rate changed over time, we can constrain the properties of this mysterious force. Does it behave like a simple cosmological constant, or is it something more dynamic? Baryon acoustic oscillations help provide the answer. This elegant connection ties the physics of the ultra-early universe directly to the large-scale structure we see today. The same sound waves that once reverberated through the primordial plasma now govern the statistical spacing of galactic superclusters. It's a direct link. A measurable bridge between the quantum ripples at the beginning and the grand architecture of the cosmic web. In the subtle clustering of galaxies, we're reading the fossilized music of creation. The first billion years were a dark age for the universe, a literal one. After that first light faded, things went quiet. For millions of years, it was just this expanding cloud. Hydrogen and helium gas, all neutral, no stars, no galaxies, just darkness. And that dark matter structure was already there, holding everything, gathering matter. But it was waiting for a spark. That spark was the cosmic dawn, the first stars turning on, and these stars were nothing like ours. They were monsters. Made from just hydrogen and helium, they grew huge, hundreds of times the mass of our sun. Their lives were short and incredibly bright. They flooded everything with a new kind of light, a harsh ultraviolet light. And that light didn't just shine, it changed things. It started tearing electrons away from all that neutral hydrogen filling space. That process is reionization. It's like a sunrise so powerful it burns off the fog. The universe was turning from a neutral, opaque sea back into a transparent, ionized plasma. This reionization epoch is a critical chapter. But we don't understand it well. It wasn't gentle, it was patchy, chaotic. Those first stars and early galaxies flickered on in isolated pockets inside that dark matter web. And around each one, a bubble would form, a bubble of ionized gas, a clear spot in the fog. More stars ignited, and these bubbles grew. They started to overlap. They merged until eventually the fog was gone, but this created a feedback loop. That intense radiation didn't just ionize the gas, it heated it. And when you heat gas, gravity has a harder time pulling it together to make new stars. So the act of lighting up the cosmos might have actually stifled star formation in the smallest, earliest galaxies. It could have regulated how structure itself grew. The key question is how. How did these first fragile structures influence reionization? And then, how did the wave of reionization influence which galaxies could form? It's a cosmic chicken and egg puzzle, played out over hundreds of millions of years, and we've been blind to it. It's the final observational frontier. Seeing into this time is the main mission for the James Webb Space Telescope. Webb isn't just looking for the first galaxies, it's looking for them in the act. Catching them reionizing their surroundings. to map how the cosmic web went from a dark matter skeleton to a glowing network of galaxies. By studying the light from the most distant galaxies, Webb can analyze their spectra. It can look for signs that their light has been partially absorbed by patches of that leftover neutral hydrogen, the last bits of the fog. That lets us watch a time lapse in effect of the cosmic dawn, to see the lights switch on one by one, then in clusters, until the whole cosmic landscape was lit. Understanding this epoch is essential. It's the bridge between the simple, smooth universe after the Big Bang and the complex, structured one we live in now. It's when that silent scaffolding first started to sing with light. The universe around us wasn't predetermined. It came from a kind of conversation, a dialogue between pure chance and ironclad law. The quantum seeds for everything were random. There was no plan for which spot would be denser. It was a cosmic roll of the dice at the very start. But once those random numbers were set, the rest became almost inevitable. The laws of physics took over. They're deterministic. If you have a specific starting point and you know the laws, the future is, in principle, calculable. Gravity doesn't care where the overdensity came from. It just sees the mass and pulls. So the cosmic web, with its specific filaments and voids, comes from this partnership. Randomness gave the unique blueprint. Determinism was the construction crew that built it over billions of years, and that leads to a question about our place. Was our particular universe, with this specific arrangement of galaxies, destined to exist? The answer is yes and no. No, because the initial quantum seeds weren't fated. In a different role, the warm and cool spots in the ancient sky would be elsewhere. The great attractors, the vast voids, they'd be in different places. Our local group of galaxies might not have formed. But yes, because once that random pattern was frozen in, the growth of structure was written into the laws. If you rewound our universe to that first instant and played it forward with the exact same starting point, you'd get the Milky Way. You'd get the Virgo cluster, the Laniakea supercluster. You would get us. The outcome was locked in by physics from that moment on. This mix of chance and necessity changes how we see cosmic history. It means the laws of physics are universal, but the specific reality we live in is just one possibility. One realization from a vast ensemble of potential universes that could have come from the same rules. Our home is both a masterpiece of physical law and a grand cosmic accident. We're here because a particular set of quantum dice fell a particular way, and then gravity spent 13.8 billion years following the instructions. This perspective doesn't diminish the wonder, it deepens it. It means in the pattern of the cosmic web, we're reading a story that's uniquely ours, but governed by principles that are truly universal. The search for understanding becomes a way to listen to that ancient conversation, still echoing in the spaces between the stars. This cosmic story, from random whispers to grand design, can feel distant. But it's not locked away. It's a story you can help write. Mapping the cosmic web is a monumental task, far bigger than any single team, and this is where citizen science changes things. Projects like Galaxy Zoo started with a simple idea. Astronomers had millions of galaxy images from automated surveys. Computers could find them, but they struggled with classification. Is that galaxy a spiral or an ellipse? Is it merging? The human eye, with its pattern recognition, is still the best tool for that. So the scientists invited the public to look. Hundreds of thousands of people logged on, school children, retirees. They spent minutes at a time sorting galaxies. What began as a way to handle data became a global collaboration. These volunteers, these cosmic cartographers, have classified millions. Their collective effort has led to real discoveries. They've found rare objects, overlapping galaxies that create gravitational lenses, peculiar galaxies that challenge our models. This work feeds directly into understanding how galaxies evolve within the large-scale structure. It turns passive awe into active participation, and that spirit extends further. Major observatories now routinely release their data to the public, the stunning images from Hubble, the deep fields from Webb, the immense maps from the Sloan Digital Sky Survey. They're online, available to anyone with curiosity. Amateur astronomers, students, artists dive into these archives. They process the raw data, creating new visualizations. They spot anomalies. They create art that translates cosmic scale into human emotion. This isn't just about access. It's about democratizing discovery. It acknowledges that the next great insight might not come from a PhD. It might come from a programmer, a teacher, an artist looking at the sky with fresh eyes. The universe becomes a shared canvas. When you contribute to classifying a galaxy or explore a public data set, you're doing more than a task. You're touching the cosmic web itself. You're adding a single day to point to humanity's grand map, connecting a personal act of curiosity to the 13.8 billion-year narrative of structure formation. This transforms the feeling of smallness into a feeling of connection. The scale is no longer just intimidating. It becomes an invitation to join a species-wide project of understanding. The story of how tiny ripples became everything is no longer just something we are told. It's something we can all help uncover, one galaxy at a time. Mapping the cosmic web isn't just about discovery. It's an engine for invention. To catch those faint whispers from the edge of time, you need machines of incredible sensitivity. And that demand, it pushes boundaries. It spins off technologies that end up reshaping daily life. Take the cosmic microwave background. That ancient glow is just a few degrees above absolute zero. To map its tiny imperfections, scientists needed amplifiers with almost no internal noise. So they developed superconducting devices, cooled them to near absolute zero. That pursuit of ultra-low noise electronics, it directly advanced the technology in modern MRI machines. The same principles that let us read the universe's baby picture now let doctors see inside the human body. They diagnose illness, they save lives. It's a connection from the coldest reaches of space to human health. Then there's the hot gas in galaxy clusters. It tells its story in X-rays, but our atmosphere blocks that light. To study it, we had to put telescopes in space. Building an observatory like Chandra required breakthroughs. Precision optics, detector design, crafting mirrors that could gently guide high-energy X-rays to a focus. That was a monumental challenge. The grazing incidence optics that came from that, the advanced CCDs developed for these missions, they found new purpose. In security scanners, in industrial quality control to inspect microchips, even in medical imaging, providing clearer views with lower radiation doses. The drive to see the violent hearts of galaxy clusters gave us better tools to see microscopic structures here at home. Maybe the most pervasive spin-off comes from the data itself. Cosmological simulations track trillions of particles. They generate petabytes of information, analyzing cosmic microwave background maps or the three-dimensional positions of millions of galaxies that requires immense computing power. Sophisticated algorithms to find patterns in the noise. Handling this deluge of cosmic data drove advances, parallel processing, data compression, machine learning. These computational tools forged in cosmic inquiry, they now power our internet search engines, the weather models that predict storms, the artificial intelligence that helps develop new materials and medicines. Simulating the universe honed our ability to model complex systems, global climate, protein folding. It's a feedback loop. Curiosity about our cosmic origins forces us to invent new ways of seeing, new ways of thinking, and those inventions ripple back through society. They solve earthly problems. They open new frontiers. It shows a truth. When we reach for the stars, we don't just learn what's out there. We learn how to build a better world right here. The technology that maps the dark matter web, that captures the X-ray glow of a distant cluster, it isn't separate from daily reality. It's a branch of the same tree, growing from a human need to understand our place in the story. Each advance in our cosmic vision leaves a tangible legacy. Woven into the fabric of modern life, that journey from a quantum whisper to the cities of galaxy clusters is one unbroken chain. It's the most sweeping story science has ever told. A cosmic epic written across 13.8 billion years. The opening chapter was written in quantum mechanics. In the first fraction of a second, during inflation, random energy fluctuations were stretched. From a subatomic scale to a cosmic one, they became a faint, frozen pattern of ripples in spacetime. That was the universe's first draft. The next chapter was written in light. As the cosmos cooled and became transparent, that pattern was etched permanently into the cosmic microwave background. That ancient glow is our Rosetta Stone. It shows us the exact blueprint of those primordial ripples, warm spots and cool spots, mapping the seeds of all future structure. Then the main character takes over. Gravity, but gravity needed a partner to work so efficiently in the early universe. That partner was called dark matter. Unseen and unaffected by light, dark matter began clumping first. It wove an invisible scaffold, a gravitational framework, following the instructions in that ancient blueprint. With the framework in place, ordinary matter could follow. Gas flowed into these dark matter wells. It cooled, condensed, and ignited. The first monstrous stars blazed to life, ending the cosmic dark ages. Their brief, brilliant lives forged the first heavy elements and began reheating the cosmos. Then the process of assembly truly began. Hierarchical merging, small dark matter halos and their protogalaxies drew together. They merged. They built larger and larger structures over billions of years. Like tributaries feeding great rivers, these mergers created galaxies, then groups of galaxies, and finally, at the intersections of the growing cosmic web, the titanic galaxy clusters. All of this construction happened on a stage that was itself stretching. The universe has been expanding since its first moment. For most of cosmic history, gravity's pull was strong enough to overcome this expansion locally, allowing structure to form. But in the last several billion years, a new force has taken the lead: dark energy. Its relentless push is now accelerating the expansion. It has put a brake on the growth of the largest structures, isolating the great clusters in a sea of stretching space. This narrative is a staggering synthesis. It weaves together the physics of the unimaginably small, quantum mechanics, with the physics of the unimaginably large, Einstein's theory of general relativity. It connects the behavior of fundamental particles to the birth of stars and the architecture of the universe itself. This is not a collection of separate facts. It is a single, coherent story of cosmic evolution. Each piece of evidence fits into this overarching framework, from the minute temperature variations in the microwave background to the vast shock waves in colliding clusters. It represents one of humanity's greatest intellectual achievements, a story we deciphered by learning to read the sky. The universe's story is one breath. It stretched across billions of years. It started with a whisper in the quantum foam, a small imperfection that got magnified to a cosmic scale. That whisper became a blueprint. It froze into the first light. Gravity, read that blueprint. Gravity is patient, it's relentless, and it had a partner, dark matter. Unseen, together they spent eons pulling matter, pulling it into wells and filaments. They built the cosmic web, the vast cosmic web. Inside that web, the first stars ignited. They forged the elements for everything that would come later. their descendants gathered, they formed galaxies, and galaxies merged, they became the clusters we see. These massive, titanic clusters, from a quantum fluctuation to a supercluster, it's one chain, cause and consequence, it's all connected. The physics for an atom is the same physics that shapes a supercluster. The laws are elegant, they're universal, and we can know them, we can trace this journey. We can hold the universe's baby picture in one hand, and in the other, a map of its grown-up cities. That's a testament to human curiosity, to ingenuity, and it places us inside the story, the calcium in our bones, the iron in our blood. Every atom heavier than hydrogen was forged in stars that formed because of those first ripples. We're not just observers of this architecture. We are part of its construction. We are the universe grown complex enough to look back, to contemplate its own origins. That understanding changes a glance at the night sky. Those aren't random points of light. They're nodes, glittering nodes in a vast, living web. They're the current chapter, a story still being written. New telescopes are coming, James Webb, Euclid, they'll peer deeper, they'll turn the page, they'll show us the first galaxies lighting up the dark, they'll map the dark matter skeleton. Map it with new clarity, the next revelations are waiting, they'll refine the story or surprise us with new plot twists.